Hey guys, so today we're going to go one step further and we're going to learn how to combine half reactions into a balanced overall reduction and oxidation reaction. In order to do this, what we're going to have to first do is recognize that these reactions are always going to be balanced in either an acidic or a basic solution. And the reason for that is because we need to make sure that we have accounted for the number of oxygens, hydrogens, and electrons present in the overall reaction. So what we're going to do today is we're going to take a look at balancing oxidation or reduction reactions in acidic solutions. Now there are really two techniques that people can use to balance oxidation or reduction reactions. The first one is called the oxidation number method. Now I'm not going to teach you the oxidation number method, but you'll probably see it in textbooks or other videos elsewhere. The technique I use is the half reaction method. Now the half reaction method is important for me because it encompasses both the things that we've talked about already and also the things that we're going to talk about later in the year in electrochemistry. There are a series of steps that are necessary to go through, and you have to do it in the right order for the half reaction method to work. So let's go through those steps and talk about why they exist in that order. So let's talk about each step individually. Now the first step to balancing a redox reaction is going to be we need to identify the oxidation numbers of every atom within each compound in the reaction. Now, we've already talked about why this is important. You need to be able to identify oxidation numbers to see which ones are changing over the course of the reaction. Now, the reason we're going to do that is we're going to identify next what is being oxidized and reduced. The thing which is losing electrons is being oxidized, remember oil, and the thing that is gaining electrons is being reduced, remember Rig, so oil, Rig. All right, or Leo says Gur, or Olay, if you like it that way. Now, in the end, we need to make sure we separate the half reactions out. Now, we've already learned how to do that, but as a reminder, we take the things that are being oxidized in every compound that exists in, and we put that on the oxidation half reaction. We take the thing that's being reduced in every compound that it exists in and put on the reduction half reaction. Now, once they're separated, we can go to balancing each half reaction independently. So we're going to do that. We're going to start by balancing the oxidation half reaction. We need to first make sure that the non-hydrogens and non-oxygens are balanced. So let's say there's a random metal sodium in there. We need to make sure the sodium atoms are balanced first. We do that by changing coefficients just like we always have. Once we get the non-oxygen and non-hydrogen atoms balanced, we then are going to balance the oxygen atoms by adding water molecules. We balance with water molecules because of the fact that these are all in aqueous solutions, which means water is already there, so we can use it in the balancing. Now, once we've added water to balance the number of oxygens, we balance the number of hydrogens with hydrogen ions. So these are the H+ ions. And this is where that acidic solution balancing comes in. H+ represents an acidic solution. So when we balance with H+, what we're suggesting is that we have acidic ions present. So once we're balanced for the number of hydrogen ions, what we are not balanced for is the charge. And in order to balance the charge, we have to add electrons. Remember, electrons are negatively charged. So if one side is positively charged and the other side is neutral, we actually have to add the electrons to the positively charged side in order to make it equal to the other side. So we are balanced for one half reaction. We then do the exact same thing to the other half reaction. So once we've balanced both the oxidation and reduction half reactions, we have to look at the number of electrons. Just like you can't have more atoms on one side of a balanced reaction than the other, it's the same thing with electrons. If the number of electrons in both balanced half reactions is not equal, you have to make it equal. And the way you make it equal is by multiplying to get each half reaction's number of electrons up to a least common multiple. That means that if you have to multiply the oxidation half reaction by 2 and the reduction half reaction by 3, you're going to do that and you're going to multiply both the number of electrons and everything else in those compounds or in those half reactions by the same factor. So we end up, in the end, with two balanced half reactions that have the exact same number of electrons gained and lost. One thing to be aware of, and we talked about this in the half reaction video, is you have to make sure that if you're dealing with the reduction half reaction, the electrons are on the reactant side, And if you're dealing with the oxidation half reaction, the reactants, or the electrons are on the products side. All right, so now once we've gotten the same number of electrons, we can combine. We combine all of the half reactions together. So everything that was on the reactant side of each goes on the reactant side of the balanced equation. Everything that was on the product side of each goes on the product side of the equation. And what we end up with is this mess of a million different things. This is when we combine and cancel. So if we have the same things, let's say water molecules, on reactants and product side, we can cancel them. Let's say we have water molecules more than one on the product side, we combine them. In the end, what we end up with is an overall balanced chemical equation. This balanced chemical equation will be balanced for atoms, for electrons. So what we're going to do now is we're going to go through some example problems, and then I'm going to have you guys try some on your own once we do that. All right, so we're going to start by doing a practice problem. Now, in this example practice problem, what I'm going to do is I'm going to take you through each of the steps individually. All right, and then I want you to follow along as I'm going through it. So the first step, remember, is we look at our overall reaction and we write the oxidation numbers of every atom in the reaction. So let's start by doing that. So I've written the oxidation numbers of every atom within this reaction. Now, if you don't remember how to write oxidation numbers, make sure you go back and rewatch that video. But here we've got the oxidation numbers. The second step is always to identify the thing that is being oxidized and the thing that is being reduced. Now, if we look for the thing that's being oxidized, remember that is the thing that's losing electrons, which means that its oxidation number is getting more positive. In this situation, we look at it. We have sulfur going from -2 to 0. So the sulfur goes from -2 to 0. It is being oxidized. So we know that the sulfur is being oxidized. Meanwhile, if we look at our nitrogen going from +5 to +2, it has gained electrons, therefore it has been reduced. So we know what's being oxidized and what's being reduced. We're now going to separate into half reactions just like we have before. So we write our oxidation reaction including not just the thing that's being oxidized, but every compound that's in it. Now I've included the copper as well because remember when we're talking about balancing half reactions, we need the copper to remain in the overall equation. You can't just eliminate it from the equation. So it's going to stay in the half reaction even though its oxidation state has not changed. Now we're going to look at the reduction half reaction. So there's our reduction half reaction. Now we need to start balancing these. So remember, the first step in balancing is we need to balance the non-oxygens and non-hydrogens. In this case, we have one copper on each side and one sulfur on each side, so we're okay. No balancing needed. On the reactant side and the product side of our reduction half reaction, we have one nitrogen, which means we're also balanced. So that step's okay. We don't need to go through that extra step, so we can move on to the next one, which is balancing for oxygens. So we're going to balance this one for oxygens. Well, there are none. So it's already balanced for oxygens. That's convenient. So we don't have to do anything to this one for oxygens. However, this one, there are 3 oxygens on the reactant side and only 1 on the products. We need to add oxygen through the addition of water molecules. So we're going to add, in order to balance the oxygen, we're going to add 2 water molecules to the product side. We've added 2 water molecules to the product side. Now we're balanced for oxygens, 3 on the left and 3 on the right. But what we're not balanced for is hydrogens. Notice how we have no hydrogens on the left and we have 4 on the right. That means we need to add 4 hydrogen ions to the left. Meanwhile, in our oxidation half reaction, we didn't add any oxygens, there are no hydrogens, so we don't need to balance for oxygens or hydrogens in this situation. It's already balanced for both. So still no changes needing to be done here. Now we balance for charge. We balance for charge using electrons. If you look at our oxidation half reaction, we have a total charge of 0 on the left and a total charge of +2 on the right. Now, in order to balance for charge here, what that means is we are going to have to add 2 electrons to the product side of this half reaction. I'm going to do this underneath just to save some space. 2 electrons. On the reduction half reaction, notice how the total charge on the left is going to be +3. Be careful here. I know we have 4 hydrogen ions, those are each +1, but we also have this 1 nitrate ion that's -1, so our total charge here is +3. On the product side, it's 0. So in order to balance +3 and 0, we need to add 3 electrons to the reactant side. Now remember, to double check that you've done it right, oxidation is loss of electrons. That means the electrons are going to be on the product side. Reduction is gain of electrons. That means the electrons are going to be on the reactant side. In order to combine these half reactions, we have to make sure that the number of electrons lost is equal to the number of electrons gained. In this case, it's not. So we need to do something. And what I said is you need to balance now the number of electrons by finding the lowest common multiple. 2 and 3 have a lowest common multiple of 6. In order to get to 6, what we have to do is we have to take the oxidation half reaction and multiply the entire thing by 3. We have to take the entire reduction half reaction and multiply it by 2. Once we do that, we can rewrite the half reactions. So let's do that. Okay, so now I've rewritten both half reactions, and notice how 6 electrons and 6 electrons are now equal. This means we can recombine them into an overall reaction. So what I'm now going to do is I'm going to recombine them into an overall reaction. I'm going to combine and I'm going to cancel. I'm going to do all of this in one step. So anything that's on both the reactant side and the product side, I can cancel. Anything that's only on the reactant side, if there are multiple of them, I can combine them together, and same goes for the product side. So let's do that. I'm going to keep things in red and blue depending on which side of the reaction they come from, and what I'm going to do is immediately after writing it, I'm going to cross it out to make sure I account for every single compound in the overall reaction when I'm rewriting it. Now, once I have done this, you'll notice that the only thing that was on both sides were the electrons. So those canceled. Everything was accounted for in the overall reaction down in our combined reaction. All right? So again, I like to sometimes cancel it out as I go through. That's a really convenient way to do it, although you certainly don't have to. I just like to make sure I've accounted for everything. What you're then going to do is rewrite an overall balanced redox reaction. Now that's a lot, but we still need to make sure it's actually truly balanced for both number of atoms on each side, but also for the overall charge. So let's do that real quick as a final check. There are 3 copper atoms on the left side and 3 copper ions on the right. So we're good for copper. Sulfur, there's 3 on the left and 3 on the right. Hydrogen, 8 on the left, 4 waters, which means 4 times 2, 8 on the right, 2 nitrogen on the left, 2 nitrogen on the right. We have 6 oxygen on the left, plus 2 and 4, so that's 6 on the right. So we're balanced for atoms. Now let's check charge. Hydrogen, each one has a plus 1 charge. There's 8 of them. That's plus 8. 2 minuses. That means a total charge on the left of plus 6. That means on the right, it also needs to be plus 6. So let's check. Well, 3 times 2 plus, that's plus 6, and no other things in the reaction have charge. Therefore, we are balanced not just for the number of atoms, but also for the charge. Now, this half reaction method does take some time. But if you can understand the steps, not just in terms of step by step by step, but truly understand why you do each step, it's key. If you did not remember why you balance oxygens and hydrogens, you might look at the oxidation half reaction and say, I don't know what to do, because you didn't have to do those steps. So understanding why you do each step is critical. In the next part of this video, I'm going to give you a problem that I want you to try on your own. All right, so now that we did an example problem together, here's a problem that I want you to try on your own. So pause the video, try the problem. If you get an answer or if you get stuck, unpause the video and we're going to work through it together after the pause screen. All right, so now you've had a chance to work through it on your own. Let's go ahead and go through it together. First step, remember, assign oxidation numbers. Now, once our oxidation numbers are assigned, we can identify the thing that's being oxidized and the thing that's being reduced. So manganese started at +7 and went to +2. That means it gained electrons, which means it was reduced. Iron went from +2 to +3. That means it lost electron, which means it was oxidized. We're going to now separate into our half reactions, and we're going to write the unbalanced half reactions. Now that our half reactions are written, we're going to go ahead and balance. We're going to start by balancing the non-oxygens and non-hydrogens. Iron's already balanced, as is manganese, so we don't have to worry about doing any coefficient work there. However, once we start having to balance the oxygens, there are no oxygens here, so that's balanced, but the manganese here has 4 oxygens with it, which means we need 4 oxygens on the product side. We do that by adding 4 water molecules. Now, once we've added 4 water molecules, we're no longer balanced for the number of hydrogens, so we need to add 8 H+ ions to the reactant side. Now we're balanced for the number of hydrogens, but not balanced for charge. In fact, we're not balanced for charge in either half reaction. So in our oxidation half reaction, we need to add 1 electron to the product side. And on our reduction half reaction, you'll notice that our total charge on the left is +7, and our total charge on the right is +2. That means we need to add 5 electrons to the reactant side. Now, remember, to combine these two back together, we have to make sure the number of electrons gained and lost are equal. In this case, only 1 electron is lost, but 5 are gained. They aren't equal. In order to make them equal, we have to simply multiply the oxidation half reaction by a factor of 5. So I'm going to go ahead and do that. We rewrite it with a full new reaction. So recombining these, we're going to again make sure that we keep everything in order. So I'm going to use the same colors I used to write this, but I'm going to cross out anything that I've written down just to make sure I kept it. Okay, so I've rewritten the whole thing combined. I've crossed out everything. I've accounted for everything. There's nothing left unaccounted for. I look across and I say, okay, is there anything on both sides that I can cancel? The answer is yes, electrons. So I've canceled the electrons. Is there anything else I can cancel? The answer is no. But is there anything I can combine? Well, in this case, also no. So now what I can do is rewrite my overall balanced redox reaction. Okay, so now that I've written my overall reaction, I need to double check to make sure everything's balanced. 5 iron atoms, 5 iron atoms. 8 hydrogen ions, 8 hydrogen atoms. 4 oxygens, 4 oxygens, and now we check charge. Be careful here. 10 plus 8 plus, that's 17. But there's a -1 here that you have to account for. That's going to be a total charge of +17 on the reactant side. That means our total on the right side also needs to be +17. Well, 5 times 3 plus, that's 15, plus 2, that's also 17. So we're balanced for atoms, which means we're balanced for mass, and we're also balanced for charge. We have overall balanced this this overall redox reaction, and there's our result. So that wraps up today's video. Let's do a quick recap. This video essentially taught one technique, But this is a really critical technique for you guys to understand this year, and that is how to balance reduction and oxidation reactions in an acidic solution. In the next video, we're going to talk about how to do the same type of balancing, but instead of in an acidic solution, we're going to try to do it in a basic solution. So make sure you're solid on this technique, because the basic solution uses the same steps and then adds a few on the end in order to make sure that we're doing it in an alkaline or basic solution. So I'd like to thank Olivia Holbrook and Emily Bakari for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.